Hello everyone, welcome to the last video of our Quantum Field Theory 1 series. I'm so excited that we're at the end right now, which is of course going to be a new beginning. So we are actually now finished with our first Quantum Field Theory series. Now, this series is really important to me, and I'm really proud, I'm really proud and glad that that we finished this series, because it's been a year, actually, like more than a year since I've made that first Quantum Field Theory 1 video on deriving the Concordant Equation from the Lagrangian density, which did really well, and it was a really great video, and we've just come a really long way. So yeah, I'm just looking at all those videos, all the takes, all the bloopers, all the learning I've done, all the learning that you all have done as well, of course. Just makes me really happy that we have put a closed knot onto this series. So here is going to be a summary of everything that we've learned so far, because it's very easy to get lost in the math and forget what we're actually doing or how some video fits in with the context of our entire series. So this video will be a great way to sort of recap all that we've done so far. So without any more further ado, let's actually begin. So, what is quantum field theory anyways? I never actually said what quantum field theory is, I think, in the series. Well, quantum field theory is the study of mathematical objects called quantum fields, no kidding, and their possible interactions. So we haven't actually done interactions yet. We've studied free fields throughout this entire series. You'll hear me saying free scalar field, free spinor field, and so on, right? We are dealing with fields that don't interact, meaning that the particles don't interact. Particles don't repel or attract or decay or create new particles. Here, with the free fields, they're very simple because their behavior is very intuitive-ish and well understood, since there's no messy interactions going on, right? So in our series, we turn interactions off, but we could also describe interactions, which we will be doing in Quantum Field Theory 3. This is 1. So, what is particle physics? Well, most of particle physics is the application of quantum field theory. Now, we can, of course, in principle, describe particle physics without quantum field theory. We could, of course, invent a new theory, which would be really great to do, which I hope to do myself, to describe particles. But what's usually taught in schools is using quantum field theory to describe particle physics, because it's a very successful theory. So everything that we learned so far has direct applications to particle physics. To know particle physics, you have to study quantum field theory. So here are all the videos that we've actually covered. I think 17 videos in our Quantum Field Theory 1 series. We started off with deriving the Concordant Equation. I forgot to finish that equation part. We'll do an equation in a highlighter. So you notice that I mentioned the free scalar field for the most part throughout this video. Throughout this whole series. Some of you guys may be discontent with that. And most fields, most of the interesting fields are spinor fields, gauge fields. There are whole books dedicated to gauge fields. Not many books dedicated to scalar fields. So you might be why are we studying scalar fields so much? The answer is that scalar fields are the most simple field, and all the other fields are pretty much spitting images of scalar fields. Like the Dirac spinor field, the Maxwell gauge vector field. All of those actually have parts of the scalar field embedded in them. And we saw them when we solved those equations. So to understand the spinor field and the gauge field is to understand the scalar field. which is why we put a lot of stress in the scalar field, and it's just easier to work with. So, and it's a cool field anyways, right? So the scalar field is pretty awesome, and it also describes pions. The scalar field famously describes the Higgs boson. The Higgs boson is the only known scalar particle in the standard model. So we can use scalar fields to describe the Higgs boson, and like how like mass emerges through spontaneous mass generation, and spontaneous symmetry breaking, which we haven't covered yet, but we will very soon. So yeah, that was the first video, deriving the Concordant Equation from the Lagrangian density. And then on to the second video, we solved that equation. An important video to watch is the Chronology Equation for the free particle, since we reference that a lot, and those equations are very similar. You guys can read the rest by yourself. We just did some more stuff. We did the Dirac Equation. Then we did Noether's theorem. The Noether's theorem videos are very important. I can't stress how much important they are. Because with Noether's theorem, we actually motivate the formulas for the Hamiltonian. We'll just really derive the formulas for the Hamiltonian, for the momentum operator, for the charge operator, which we'll be using so much in the future. So that's why we did a brief detour to Noether's theorem, because it helps us a lot in forming expressions. And it's a pretty beautiful theorem that links symmetries with conservation laws. So that conserves the environment, you know? So then we did the Crockett equation. That video was particularly kind of weird. Kind of weird and hard, because the Crockett equation is not really taught that much. So when I was learning the Crockett equation, I was like, this is a really weird equation. It's like the Maxwell equations, but with a mass particle. And mass particle, that's kind of weird, right? So the Crockett equation, really cool equation, and it describes the weak force. So all the equations that we've done so far, they describe something real. We haven't done hypothetical models. Like some people will talk about a quantum gravity field, which would be a spin 2 vector field that describes gravitons, right? But we haven't really talked about that yet, because we don't know if gravitons exist. So all the fields we talked about have direct, clear applications of particles that do exist, at least, or particles that we have evidence for their existence. So then we did the Maxwell equations, which is pretty straightforward. From the Crockett equation, just set the mass to 0, and then there are some what's it called? There are some important tidbits that we have to add, some nuances, since the massless nature of the Maxwell equations make the photon have only 2 non-trivial polarization states. So you have to keep that in mind. And then we talked about gauge theory, gauge symmetries, U1 symmetry. Again, a lot of stress on symmetries, since they're very important in quantum field theory. With the gauge symmetry, especially the U1 symmetry, we are able to derive the charge operator, the conserved quantity into the U1 symmetry. We are able to derive the momentum conjugate field, which will be used in the second quantization. And then we quantized E equals mc squared. That was a very fun short video. It took a lot of time to make that video. Really, it's 3 minutes long, but it took a lot of time because the software that I used sucks. But we made it work, and yeah, that was a great video. Then we did the solution to the Concordant Equation part 2. We derived a more practical form of the Concordant Equation that I referenced without actually explaining it. So I was like, okay, let me just make a whole video about the new form that we've been using, because the new form that we were talking about, it was an integral over just 3 of the 4 momentum components, so the integral over 3 momentum, and we had a pi, 2 pi cubed, and the square root of 2 omega k. And I haven't talked about where that comes from, but I was using it in all of these videos over here. So I decided that I had to make a video explaining where that comes from, and that's why we have a second video to the Concordant Equation solution. Alright, so then the Casimir effect. I was really happy and excited to make a video on the Casimir effect, because the Casimir effect, it's like the it's an application of quantum field theory. Like, so before that, all we've done is like theory, just like here's the theory, here's this theory, here's that theory. It's what the theory says. But in the Casimir effect, we're actually able to make a prediction from the theory, which is so cool. And we're able to do like half of that before actually doing second quantization. So like it can be a bit stressful sometimes. So in all this theory and not having any applications, I mean there are some applications like how the photon has only two polarization states and stuff like that. But we haven't really done like a big application like a real like effect of physical things, right? Besides like photons. So it can be stressful to like not have any applications before second quantization. So that's why we jumped into Casimir effect. We got halfway done. You derive the fields at the plates and the Hamiltonian. And that video did pretty well as well. I think it was like my fastest growing video. But then it kind of like plateaued a bit. But that's alright. But yeah, Casimir effect was a great video to make. I really had fun and I loved making that video. So after we do second quantization, then we can do much more applications. Then we can do scattering, things like that. Also, I say the word second quantization a lot. If you guys don't know what that is, that's completely fine. I've never actually explained it. Well, I explained it briefly in my past videos, but I haven't actually done that yet. So once I talk about second quantization, which is like in the next 2 videos, it will all make sense. And that brings us here. So yeah, that's all we've done. Hopefully you guys can see some of the connections. If not, well then here's more. So in quantum field theory, we start out with Lagrangians in the Lagrangian approach. So here are the Lagrangians for the Dirac equation, Dirac Lagrangian, Concordant Lagrangian, and from each of these Lagrangians, you can derive an equation that helps us solve for the fields. Now, I've never actually mentioned the Dirac Lagrangian before. Maybe I mentioned it once in my space-time algebra video, where we derived the Dirac equation, but like we haven't really talked much about the Dirac Lagrangian. And we don't really need to, since we derived the Dirac equation as a second way, or the first different way. But the Dirac Lagrangian, it's like the other ones, same game, put it in the order of the Lagrangian equations, and from that we can solve, and we can get the Dirac equation. This psi here with a bar on top of it, that's called like the spinor, the complex conjugate of the spinor field. And we can actually motivate this equation by looking at symmetries. So you guys may have been wondering, as I did, where did all these Lagrangians come from? Like, how do we know that they're right? Like, why do we use them? We could, of course, add anything we want to our Lagrangian. Like, I can make this, like, m cubed if I wanted to. And I can look at the physics that arises from that. But each of these Lagrangians can be sort of derived from looking at symmetries. Now, the question becomes, why do we look at symmetries? And to my knowledge, there's no actual greater reason. Like, we just see that in nature, there are things that are symmetrical a lot. So we're like, okay, let's just guess that there is this symmetry and see what happens. And that has been a very successful approach. Maybe one day we'll see that, hey, maybe nature doesn't really like symmetries. Maybe these Lagrangians are wrong, which many suspect them to be wrong. That kind of motivates the concept of an effective field theory, where a Lagrangian is just a low energy limit of some greater Lagrangian. But these Lagrangians are pretty successful. They describe a lot, but as many suspect, as many believe as I do, these Lagrangians would probably fail at a certain energy scale. So these Lagrangians come from, again, looking at symmetries. So for example, we can motivate the Dirac Lagrangian. My Apple Pen just died. Let me just charge it for a bit. So we can motivate the Dirac Lagrangian by looking, or really the QED Lagrangian, by looking at the U1 symmetry. looking at what Lagrangian can preserve this U1 symmetry, and the QED Lagrangian does the trick. Also, something that I have to mention is that the Praca and the Maxwell Lagrangian, it can also describe gluons, right? We've been talking about electrons of photons, but this Lagrangian can also describe gluons. All we have to do is just add a color indice. We add a color indice like in the Faraday tensor there, and that describes color interactions. Then we have to couple it as well to the color gluon field. We have to add like a coupling there. M is going to be 0, but we'll have a coupling to like the gluon field. But don't worry about that. But my main point here is that this equation can also describe gluons, and quantum chromodynamics is like very analogous to QED, but instead of electric charge, we have the color charge on the strong force. And you'd often hear like QED and QCD kind of being called Yang-Mills theories. Yang-Mills theory, those are theories that like have an SUN symmetry to them. Like the Lagrangian for quantum chromodynamics has what's called an SU3 symmetry, and we call that a non-abelian gauge theory, since SU3, the group, is non-abelian, which means that they don't commute. I made a video on the abelianness of groups, if that doesn't make any sense, but don't worry about that. That's future stuff right now. But there are so many applications of this Lagrangian, and yeah, so, and then the Praca Lagrangian describes the weak force as well. So this Lagrangian can describe so many different things, right? That's why gauge theory is a very big thing. People love to talk about gauge theories. Like there's even talk about formulating gravity in terms of a gauge theory. So like, which is why we spent a lot of time talking about gauge theories in our video series, and we will continue to talk more about those gauge theories. All right, so here are our actual equations that we solved. Here's the Praca equation / the Maxwell equation. For the Maxwell equation, we just set m to be 0. So the Maxwell equations are a special case of the Praca equation. Here's the Dirac equation. We have a plus or minus sign added there. The reason is that when deriving the Dirac equation, we are free to choose whether it's plus or minus. So we just left that in there. Here's the Concordant Equation. We should be familiar with each of these. Maybe not so much the first one, but you should be familiar with the Dirac and the Concordant Equation. So we actually solved each and every one of these equations. We solved them all. And here are the solutions. They are very intimidating, I know, but when in doubt, refer back to the scalar field for a lot of cases. Because the scalar field is sort of what builds the other field. Because we notice that, hey, look, our scalar field is a superposition of plane waves. And oh, look, so is the spinor field. It's also a superposition of plane waves. Oh, wow, so is the Praca field. Oh, and the Maxwell equation field. All of these are superpositions of plane waves. And all of these fields solve the Klein-Gordon equation. The spinor field, the vector gauge fields, they all solve the Klein-Gordon equation. So when we want to approximate a field, like the spinor field, we can approximate it as a scalar field. We often approximate the spinor field as a complex scalar field, and we often approximate the EM field as a scalar field, because in the Casimir effect that we talked about last video, we should really be using photon fields, right? But since photon fields can be a bit more complicated, we simplified it by using a scalar field, which will cause some errors at the end, but the errors aren't too big, and then we can always just solve it again for the case of a vector field. So yeah, basic idea here is that in quantum field theory, we are dealing with these fields, right? Like, these are the fields for quantum field theory. All of quantum field theory is going to refer back to these fields. So you want to understand these fields. They look very ugly in the more general form. You won't really be seeing them written like this a lot of the time. Like for the spinor field, often we will specify what the spin of the incoming electron is or something, which will simplify this equation a lot. For the photon field, we'll often specify the polarization states of the photon, which will simplify this equation a lot. So with all those techniques, these fields become a lot less scary. But again, the main lesson, the biggest takeaway here is that these fields are just plane waves. And plane waves are very easy. I don't want to be condescending, but they're easy in the sense that they are well understood. Like in classical mechanics, we see plane waves. Like take a guitar string, pluck it, plane wave. Let me just pluck my guitar right now for proof. Oh, almost fell down. Okay. Here's my guitar. If I pluck it right now, it's a bit out of tune, my guitar eddy. But when you pluck the string, you get sound, and the sound is formed by an oscillating string, which is a plane wave. So yeah, plane waves are the basis. They form our quantum fields, and they're very important stuff. So yeah, and taking their derivatives is very simple, since the derivative of e to the ix is just k. So it's ik e to the ix. Derivative of e to the x is the same thing. So yeah. Here's some cool important stuff that you might have missed. The Dirac equation can be derived by factoring the Concordant equation. And we use what's called space-time algebra in the Dirac equation derivation. It's a really cool algebra formed by the anti-commutativity of the gamma matrices. Here's an example. If you add gamma 1 and gamma 2 together, it implies that they anti-commute. Then it implies that gamma 1 equals -1. And we sort of introduce the space-time algebra to cancel out the gamma matrices from the Concordant equation when we are expanding it out, so that we can factor it. Chronology oscillations are described by the Dirac equation. We talked about this in our video on the Dirac equation, of course. Basically, a field that starts off as left chiral, when a time evolves, it becomes a right chiral field times a -I scaling factor. Mass is derived by interactions between spinor fields and the scalar field. We talked about that briefly in our Dirac equation video. This is, of course, an allusion to the Higgs mechanism. Oscillations I'm speaking too fast. Oscillations are also controlled by mass. We found out that the more mass increases, our oscillations rate, I think, decreases. Correct me if I'm wrong. Which is pretty cool. So chiral oscillations, pretty cool thing, described by the Dirac equation. So that's another prediction of quantum field theory, that the chirality of electrons can oscillate. Cool. The photon has two polarization states, which is a special case of the Pocket equation. Pocket equation speaking way too fast. Sorry. When I get excited, I speak really fast. Pocket equation describes the weak interactions. This is a really cool thing. We haven't talked about weak theory that much. We will, though. We will talk about all of the particle physics stuff. It sounds kind of funny, but we will, I promise. We will talk about lattice field theory, We'll talk about electroweak theory. We'll talk about the Higgs mechanism. We'll talk about chiral perturbation theory. We'll talk about all the really cool stuff. But we must first build the foundation. So I say a lot like, we'll talk about this in the future. And like, when is that going to come? I mean, I don't know, sometime. Maybe in the next, like, 2 months, maybe. Depends on how school is hurting me. Just kidding. But school's pretty nice, honestly. Moved to a new school. See, I started talking about, like, I get sidetracked a lot. But yeah, I actually did move to a new school. It's pretty nice. School was pretty fun, honestly. Like, except for the homework and stuff. And yeah. So the Proctor equation is, like, often ignored by physics professors in textbooks a lot, because it describes the weak theory, which isn't really that popular, right? It's pretty, I don't want to say obscure, because if you're a particle physicist, you would have learned about it, of course. But it's much more, it's really mathematically detailed. It's not a very intuitive theory, because weak decays break parity. They break what's called CP. So charge thingamajig, charge conjugation, and parity, right? And that's like people when people discover that they break CP, the CP violation, they break the CP symmetry. People are like, wow, that's so weird, dude. That's so crazy, man. So it's a really non-trivial theory. I don't want to say non-trivial, because QCD is non-trivial. I wouldn't really say weak theory is non-trivial with a strict sense of trivial. But weak theory is very non-intuitive, for sure. So that's why the Proctor equation isn't really talk about that much. But it is going to be used a heck ton in the weak theory video. And the last most important thing of cool important stuff is that y'all are awesome. So this is the end of the quantum field theory 1 video. Yeah, y'all are awesome. I like when I see a comment saying thank you for this video, it makes me really happy, and it just makes my day. Like, you guys only see the final output, the final product, the finish, right? You only see the final product of a video, but like, these videos can often take me a really long time to make. Like, sometimes because of my stutter, since I have a stutter, sometimes I'll be like stuttering a lot, and like it just kind of breaks the flow. I'd have to start all over again. So a video that should take like maybe 20 minutes to film takes like maybe up to 2 hours. So, but that's okay, since like it's very fun every step of the way. So I work really hard on these videos, and I just love just sharing knowledge, sharing things that I learned with you all. I find that explaining a topic helps me better understand it myself. For example, I didn't really understand like the Maxwell equation, like the tensor form that much, and explaining it just helped me learn it. So it's been a really great experience. Like, just sharing all of this with you guys, getting feedback, like corrections as well. Like, when you guys correct me in the comments, that's also really great, since it helps me and other people learn even more as well, which is just great. So yeah, like when I started this whole series, like I didn't know like I'll get this much traction. Like, we have 700 subs right now. When I first started this channel out 2 years ago when I was 14, I didn't like I was like, people like aren't gonna like spend their free time to watch a tensor calculus video, right? Because people don't like tensors that much. But I was wrong. Many people do love tensors, and it's just that people are afraid to teach these like high level topics, so there is a scarcity of them online. So like, I hope that like someone might see this series and be inspired to make their own series on some topic that isn't very popular on YouTube. And just like keep this whole thing going, because like when I was learning this stuff, there was like not that much videos on this content on YouTube. Now I'm seeing much more, but like I hoped that more people start making more videos on YouTube that like describe these things in very detailed sense, and just to help more people just learn, because learning is awesome. Honestly, it's great. And yeah, this is not the end of quantum field theory. I don't want to imply that. This is the end of quantum field theory 1. Quantum field theory 2, which will come sometime soon. I don't know. I have to study for my Oxford test. But quantum field theory 2 will come when I have enough time to make the video, which I kind of depends on like my circumstances, but I'll upload it like probably sometime during September, maybe September, early September, mid September, and quantum field theory 2 will focus on particles now, because we've talked about fields, but not much about particles. So we will focus a dang ton on particles and propagators. That's gonna be the name of it, the name of the series. It's gonna be quantum field theory 2, particles and propagators. So we will actually be doing second quantization in that series. 3 will focus on interactions. 4 will focus on scattering. 5 will focus on renormalization. And then 6 will focus on, I think it's path integral and non-perturbative phenomena. I think that's what 6 is on. We'll see, but yeah. This is farewell. Not farewell, I'm gonna come back. But this is the end of Quantum Field Theory 1. I want to end this series like on some like inspirational quote. I guess I'll end with a quote. This is a quote that I made, so like I just want to share it because like it's cool to end it on a good quote. The quote is, "The fool lets his past control him. The smart man lets the future inspire him. And the wise man makes his present inspire others." And I hope this video has inspired you all. Thanks for watching, and I'll see you guys later. Till next time. Bye!